Good day, everybody. Justin Miller, Rockstar College Physics. We're going to do some stuff here. So, what do we have right here? We got ourselves a galvanometer. We've got ourselves a nice little solenoid, just a coil. See right through it, right? Nothing tricky about it. Got a battery here, and then I've got some connective wire that goes through the coil, through the battery, through the galvanometer, and through a resistor. This is I think it's like 1050 or something, but nonetheless, we got something going on here. What's going to happen when I plug this in, connect this to? We've got a complete circuit, and oh look, we get a deflection of the needle because there's current being driven through the galvanometer. It reads it, and then there goes a deflection. Great. What's driving the current? The battery, of course, right? So the battery's producing some current, we're driving the current through the circuit. That's a fantastic. So let us ask a question and say, well, we know that currents produce magnetic fields, right? So can we use a magnetic field to produce a current? That's a good question. Well, let's see here. Let me disconnect this battery, completely remove it from the circuit, no more battery. We'll just take our coil here, plug that in, and look what happens. Nothing, because there's no battery in here, and all we've got is a coil connected to this. So what? Well, I happen to have a magnet right here. How do I know it's a magnet? There we go. It picks up some needles there that are iron in them. And what I'm going to do is I'm going to take this magnet and I'm going to take this coil, set the coil up there so there's no funny business going on still, just the coil. Set it up there. I'm going to take the magnet and move it around the coil like a wand and nothing happens. But what happens if I take the magnet and actually insert it into the coil? Watch carefully. Watch this little needle here. Oh my gosh, did you see it underwent a deflection while I was pushing it into the coil? Now it's inside the coil. Nothing's going on. Let me pull it on out. Oh my gosh, I got a deflection in the other direction. Those deflections are really a current, right? Current's being produced in this circuit through this coil and through the galvanometer. So I insert it, get a current in one direction, pull it out, get a current in the other direction. What happens if I go ahead and flip the magnet around? When I flip the magnet around, I push it in, now I get a current in the opposite direction that I got last time. I pull it out, I get a current in the opposite direction that I got last time. So, what do we have here? Well, when the magnetic field is not changing through the coil, we get nothing. But when there is a change in the magnetic field through the coil, we do get something. And what do we get? We're getting a current. So this brings us to what is known as Faraday's law of induction, which is all about generators and producing EMFs, inducing EMFs, if you will. So let's just go ahead and get this out of the way right here without taking up too much time, space, and such. I'm going to set it down here gently. Get rid of this. Okay. And we now proceed to look at Faraday's law of induction. Faraday's law of induction, a nice mathematical statement in a sense. It says that the induced EMF through a loop with n turns is equal to, through a loop with n turns is equal to negative n d phi sub b dt. So, let's spell out this stuff here. E sub in is the induced EMF. It acts almost like a source potential in a sense. N is the number of turns in a loop through which there is a change in magnetic field flux with respect to time. So, what is the magnetic field flux? V sub B is the magnetic field flux. Just like we had electric field flux with Gauss's law, we can have magnetic field flux. The amount of the magnetic field that crosses through some cross-sectional area under consideration. In general, magnetic field flux can be defined as E hat dot dA hat over the area in which, well, we're considering. So there's the generalized expression for flux, but we're going to look at a specific case here in which we have a loop that's in a plane, a conductive loop in a plane, and a uniformly directed magnetic field. The loop encloses an area within a plane the magnetic field is uniform across that area. Well, phi sub b becomes something pretty simple. For one, the dot product vanishes, and we can leave that with a cosine of theta, where theta is the angle in between the magnetic field vector and the area vector. And if B is uniform, it can be pulled out front, and we can we'll basically get this V A is the cosine of theta, where theta is angle between magnetic field, magnetic field's direction, and the normal of the plane of the loop. So if theta is equal to 0, we have a maximum amount of flux. If theta moves to 90 degrees, we have no flux. So let us just take a little bit of a look at that. We can take, I've got some little wire around this. This makes a nice little loop here. We've got some area enclosed by this loop. And if we have, say, a magnetic field directed towards me, uniformly directed towards me, there is some non-zero magnetic field flux through the area that this loop encloses. And right now, the normal of that loop would be aligned with that magnetic field, and theta would be equal to 0 degrees. However, if I turn the plane of the loop like this, now the normal of the plane of the loop's that way, magnetic field's this way, there's a 90-degree angle in between them, and we have no magnetic field flux, because there is no magnetic field that goes through the loop because of the orientation. So, maximal flux, no flux. And ultimately what we need in order to establish an induced EMF is a change in magnetic field flux over time through the area enclosed by the loop. That's what that statement's all about right there. Faraday's law of induction. So there's lots of different ways of doing that. We did it in the demonstration by having no magnetic field within that loop and then entering a magnet, which will increase the strength of the magnetic field over time through the loop. And what does that do? It induced a current that was due to an induced EMF. We pulled it out, magnetic field goes to 0 over time. We had a change in magnetic field flux through the area enclosed by that loop, and we got ourselves a current. So that's what we've got going on. That's one way of doing it. We could start changing the area of the loop too. Take a loop and oscillate its size. That would be one way. Or we could just change the orientation of the magnetic field with respect to the loop. And that's a pretty easy thing to do here. We could take, again, for instance, that we have a magnetic field uniformly directed towards me. And right now, we have the maximal amount of flux, the area enclosed by the loop by the strength of the magnetic field, multiplied by the strength of the magnetic field. If I start turning this loop, I start changing the orientation of the available area for the magnetic field to penetrate through, and I change the magnetic field flux. So I change it from the maximum amount to 0, and then I increase it to the maximum amount. Then I decrease it to 0, then increase it to the max, then decrease it to 0. As long as I keep this rotating in this uniformly directed magnetic field, I continue to produce a change in magnetic field flux through this loop, which will continue to induce an EMF, which will continue to induce a current if we have a completed circuit. Excuse me. So, it's ultimately how generators operate, in a sense, in that, hey, change the magnetic field flux through some loop. So here's a little box, maybe a little bit hard to see, but it's a wire loop wrapped around a whole bunch of times. I think I got it maybe 100 times or so. I got two really strong magnets, north facing south, attached to a little spindle here. And I've got some LEDs connected to the loop here that will light up if enough current goes through them in a certain direction. And what I can do is I can start spinning this magnet and change the orientation of the magnetic field through this loop. And what's that going to do? It's going to induce an EMF, which is going to induce a current, and hopefully light up these little LEDs. So what happens? Hopefully you can see that. They light up. As I spin this around, they kind of flash on and off. And making some electricity, just like that. The power. Anyways, when you go out to the desert, I'm sure you've seen those big wind turbines, and say, oh, they're producing electricity. How are they doing that? They're utilizing air to move these big blades, which inside there, there's something very much like this. A little bit more complicated, but the very basic idea is there. Change the magnetic field flux through some conductive loop, and you will induce a current in that completed circuit with that conductive loop. So that's pretty neat indeed. Let us look at that particular case where we spin something around and see if we can utilize Faraday's law of induction to figure out what sort of induced EMF and induced current we're going to get. So let's throw that there. Let's back down here. And we'll probably write that out again. That's okay. Draw a little scenario here and say that we're going to take ourselves a conductive loop. And we'll say that it's just N turns. That doesn't really matter. We're going to take a magnetic field that is uniform, constant, not changing at all over in space. So we've got some background magnetic field. Uniformly directed, constant in magnitude into the board. And what we're going to do is we're going to take this loop, attach it to some little axles here, and we're going to rotate it. Rotate the loop around. So it's basically like we're taking this and we're going to spin it around in the magnetic field and kind of see what sort of EMF are we going to get according to Faraday's law of induction. So Faraday's law of induction says that the induced EMF is equal to negative N d phi sub b over dt. We have the loop exists in a plane, which is good, and the magnetic field is uniformly directed, which is good as well. It's uniform over its area. So this can be reduced down into negative n d by dt of a b times the cosine of theta. Or that's just the magnetic field flux there, AB cosine theta. And there I wrote it, BA cosine theta, that's okay. So we've got this. So now it really comes down to what rate is this changing, this quantity here, with respect to time? Well, let's ask ourselves some questions here. We've got ourselves some area enclosed by this loop. That's not changing. We're not altering the area. What we're altering is the orientation of the loop with respect to the direction of the magnetic field. We're changing theta here. So both A and B, excuse me, A and B are constants. So what do we do with this? We can pull both of those out and have that the induced EMF is equal to negative N times A times B times D by dt, the cosine of a theta. So now it comes into this theta business. Do you see a t in there anywhere? Where's time? We need to be able to take the time derivative of this. What's changing with respect to time? Theta is. Theta changes with time as the loop rotates. So let's put a little contingency on this. Let's say we're going to let the loop rotate at a constant rate, constant angular rate. What do we have then? Well, we've got some equations, right? Equation of motion for constant angular acceleration. We've got an expression that says that delta theta is equal to 1/2 alpha t squared plus omega I times t. Alpha is the angular acceleration, omega I is our initial angular velocity. And we're saying right now that that's a constant. If it's a constant, there is no angular acceleration, so this ultimately goes to, alpha being equal to 0, delta theta is equal to omega times t, where omega is constant. So there's time right there. So what do we do with that? Well, we go ahead and put it in there. So let's pull this on down and see what there is to be seen. We're going to let theta initial be equal to 0 degrees, the orientation just like that. So at t equals 0, there's theta initial. And what do we get with this? We get that theta is then equal to omega times t. And we've got ourselves that the induced EMF is then equal to negative n a b times d by dt, the cosine of omega t. What is the derivative of cosine of omega t? That's right, we've got a sine of omega t, or negative sine of omega t, and then we got the derivative of this, we get an omega out of that, so this ends up becoming, the induced EMF is the negative signs cancel each other out, we got negative n a b omega sine of omega t. No negative, sorry, they cancel out, I just said that. There's the induced EMF. What is that? Well, this is sinusoidally varying. Let's take a look at what that actually means in terms of this EMF. So if we plotted this EMF out. What do we have? We just got something sinusoidal, right? So we could go ahead and note that we've got some maximum NAB omega and some negative NAB omega, the amplitude of the oscillations, and then we've got the oscillation itself. So up and down, and up and down, and up and down, and up and down. There we go. Sometimes the EMF is 0. 0, 0, 0. Sometimes the EMF is a maximum value of NAD omega, positive. Sometimes it's a maximum value in the opposite direction, NAD omega, negative. Sometimes it's increasing, sometimes it's decreasing. It's alternating. This is an alternating EMF. Well, let's think about what sort of current is going to be induced in this. The current induced in the loop will be, well, I induced is going to be equal to E induced divided by R by Ohm's law. All right, so it's Ohm's law restated there. So there is the induced current. Depends on the resistance of the loop. So the loop has some finite resistance. There's the induced EMF. What does that give us with the current? Well, that doesn't block that out too. Current, we've got time, and we've also got the current itself, I induced being equal to E sub IN, the induced EMF divided by R will be equal to NAB omega divided by R times the sine of omega t. Well, that gives us some maximum value of the current, NAB omega divided by R, and some negative NAB omega divided by R. And what do we get with this? Well, the current is going to go very sinusoidally. Sometimes the current is 0. Sometimes it's increasing to a max, sometimes it's decreasing down to 0, sometimes it's increasing in the opposite direction. The negative sign is just directional, right? With respect to currents. With respect to EMFs, it's the polarization, plus versus minus. With the current, it's the actual direction of the current itself. So the current just oscillates. This isn't a direct current that's produced like we've been studying prior to this. This is a current that just goes back and forth. All the electrons are just kind of vibrating back and forth sinusoidally at some specific angular rate or some specific frequency, which is correlated specifically with this omega right here. And that omega is determined by the rate that we rotate the coil at. That's determining how quickly the little oscillations of the electrons occur in the circuit. What do we do with it? We use it. We pass it through elements, through tungsten filament, and get some light, or through some stove burner and get some heat. That's what we do. But this is ultimately how you produce alternating current, one way, producing alternating current. Very naturally, easy to produce. And that's one of the main reasons why we utilize AC, because it's just so easy to produce. We run water through turbines, spin turbines, produce AC. Wind with turbines produce AC. So that's not the only reason why AC is primarily used in transmission, but it's one of the reasons. Nonetheless, this is it. This is the beginning of generating electricity. It's a powerful thing. We depend on it in our daily lives at this point. So what else could we say about this? I think that'll be about it for right now. We'll come back and we'll look at some stuff as time goes on. All right. Thank you.